Dear students, in this short video, we will discuss impulse response and convolutional integral used in the analysis of continuous time, linear time invariant systems. At the end of this video, some questions from the previous examinations conducted by IKG Punjab Technical University will be listed for the practice of the students. Systematically organized course videos are available at drsatvir.in along with the PowerPoint presentations. The link is given in the description. Before starting with the convolutional integral, let us recall some definitional issues related with the continuous time LTI systems. Linear time invariant systems, that are also known as linear shift invariant systems, which belong to a class of systems whose output for a linear combination of inputs are same as the linear combination of the individual responses corresponding to those inputs. Secondly, the output does not depend upon when the input was applied. These both characteristics of the LTI systems make it easy to represent them graphically and analyze mathematically. By definition, the impulse response of an LTI system is the output yt when input xt is the unit impulse signal delta t. The same thing is represented over here in this figure, where input xt is equal to delta t, then output yt will be equal to ht, which is nothing but the impulse response of the system. Impulse response of the system is always represented as ht. For an arbitrary input sequence xt, the output yt of a continuous time LTI system whose impulse response is ht is determined using convolutional integral, which is given as yt is equal to integral from minus infinity to plus infinity x function of tau into h function of t minus tau into d tau. Hence, the impulse response completely defines the behavior of a continuous time LTI system. Now let us take up one numerical problem for the purpose of practice, where we are required to determine the output yt of an LTI system whose impulse response is ht is equal to e raised to power minus 3t ut, and the input is unit step signal ut. Now let us consider xt and ht in this relation and modify the limits accordingly. We will get yt is equal to integral from 0 to t e raised to power minus 3 tau u tau into u function of t minus tau d tau. On integration, we will get e raised to power minus 3 tau upon minus 3 with the limits from 0 to t. Putting the values of the limits and simplification, we will get output yt is equal to 1 upon 3 into 1 minus e raised to power minus 3. Now let us consider the properties of the convolution integral. The first property is the commutativity property, according to which we can exchange the position of xt and ht and the resultant will remain same. The next property is the associativity property, according to which we can convolve more than two mathematical functions irrespective of their groupings done using parentheses. The same thing is depicted in this equation mathematically. The third important property of the convolution integral is the distributivity of additions property, according to which we multiply each term inside the parenthesis with the term outside the parenthesis. Fourth property of the convolution integral is the identity property, according to which if we convolve any signal xt with the impulse signal delta t, we will get the signal xt as it is. Now let me conclude this video by listing these questions from the previous examinations. These are 11 questions classified as lower order thinking skill based questions. Those are required to be answered in short. And these 4 questions are classified as higher order thinking skill based questions, and it is my personal advice to the students that they must go through these problems and try to solve them on their own. In our next video, we will discuss the transfer functions, which is a frequency domain representation of system response. Till then, keep learning, keep sharing.